This is lecture 29. Today we'll be talking about energy, heat, and work. So we actually care a lot about the energy that's released during a reaction. We care because we use this energy from reactions to power our world. So this includes fossil fuels, right? The combustion reaction that happens in the engine of your car. In batteries, this is the transfer of electrons from one metal to another generally, or from one ion to another. So any way we generate power is based on some sort of chemical process, some sort of motion of electrons, some sort of rearrangement of atoms. We want to be able to understand each of these processes well enough so that we can improve upon them, right? If you're going to improve how well your fuel performs, you have to first understand how your fuel performs, right? You have to understand what's going on, what reactions are involved. And so this study of the energy of a reaction and the heat associated with it is what we call thermodynamics. There's some rules that go along with thermodynamics. The first of them is what we know as the first law of thermodynamics. And that just says that the change of energy of the universe is zero. So even if you have a reaction that explodes with huge energy, let's say an atomic bomb going off, that is still not actually changing the energy of the universe. You've just moved the energy from one place, in the case of an atomic bomb, from the nuclei of the atom. You've moved it from the nuclei to the surroundings, but the universe still has the same amount of energy. So put more succinctly, die Energy der Welt ist constant. Now, I don't speak German, so maybe you could pronounce that a little better than I could. But basically, the total energy of the universe is constant. This is what we often call the law of conservation of energy. Now, we talked about at the beginning of the semester how there are three forms of energy. We can review those now. So first, there's radiant energy, which basically is just light. So light radiates from place to place. Then there's also potential energy, which is energy stored in an object due to its position. So the most common way we think of potential energy is in the form of gravity. If I hold something up and I drop it, then it can convert its potential energy into kinetic energy, which is the energy of motion. However, in chemistry, we often don't worry too much about gravity, but we more about composition, which is the position of atoms relative to each other and how that affects their potential energy. So these second two, potential energy and kinetic energy, exist at the atomic and molecular scale. And to understand thermodynamics, we're really going to have to understand these two types of energy. Now, potential energy, all right, like we said, it's just energy due to position. In chemistry, we're going to be talking about certain contexts for chemical or for potential energy, and so we give it a special name, which is chemical potential energy. And in this context, we're always thinking about potential energy stored as a function of where the atoms are to each other. So one place that this potential is stored is in chemical bonds. So for example, if I've got oxygen molecules here reacting with a methane molecule, those can burn in a combustion reaction. And what we're doing is breaking a bunch of high energy bonds to form a bunch of lower energy bonds. So when we go from a bunch of high energy systems to a bunch of low energy systems, we have extra energy left over, and that's given off in the form of light and heat that's passed in the surroundings, right? So we're converting that potential energy into other forms of energy. The other place that chemical potential is stored is in electrostatic interactions. So here I have a drawing of a salt, right? So a crystal lattice has energy stored in its interactions between ions, but this can also be referring to intermolecular interactions as well. So hydrogen bonding, dipole-dipole interactions, these are all electrostatic interactions, and so chemical potential is stored in all of those interactions, and it's going to take energy to break those interactions. All right, now kinetic energy gets a little more fun at the atomic and molecular level. So there's actually three types of molecular motion that we need to worry about. So the first is translational motion. This is the type of motion we typically think of. This is just the motion of an atom from one place to another, or a molecule translating from one place to another. So it's pretty straightforward. The next type of motion, though, is rotation. So everything, every atom, every molecule, and every planet, and every solar system, pretty much everything is rotating all the time. And at the molecular level, this becomes especially important in terms of storing kinetic energy. So every molecule is tumbling in space, and the speed of that tumble depends on the energy of the molecule. And then lastly, there's vibrational motion. So it turns out anytime you have a bond, that bond can vibrate back and forth. So you can be oscillating back and forth. You can, if you have three atoms, you can be wiggling, or you can be stretching symmetrically, or you can, oh, it's hard to do with my hand, but these atoms can be stretching asymmetrically. If you have a single bond, you can actually get rotation around that, and that rotation counts as a vibration as well. And so for a long molecule like hexane, we usually draw it as a long string, but that long string can rotate around every single one of its carbon-carbon bonds. And so that can result in it crumpling into a ball or adopting different conformations. But all of these vibrations are constantly happening, whether it's a stretch or a twist or whatever. All of these things are constantly happening. And all three of these motions, translation, rotation, vibration, are all happening simultaneously in every molecule that we're thinking about, and even the ones we're not thinking about. So we've already said temperature is proportional to our average kinetic energy, right? And we came up with an equation that related our root mean squared speed, which is our translational mode, to our temperature. But it turns out these other types of motion also are dependent on the temperature. So if you increase the temperature, you'll actually increase your rotational speed, and you'll actually increase your vibration rate. So you'll have a more or a higher frequency vibration. And actually, the way microwaves work is microwave radiation actually induces water molecules to start spinning. So as you add microwave radiation, your water molecules start spinning fast, and as they're spinning, they can then collide with more energy into other things, and that spin motion can be converted into translational or vibrational motion by that impact. Okay, now, so we've talked about potential and kinetic energy. We often want to think about all of the energy in a molecule or in a group of molecules. And so our total energy we refer to as our internal energy. So the internal energy is equal to the total kinetic energy plus potential energy, right? So that means all of our motion, whether we're a solid, a liquid, or a gas, plus it means all of the energy stored in all of our covalent bonds and in all of our intermolecular interactions. Now we have several units for energy. These aren't too bad. Well, the first one is the joule, which we've already used a little bit, right? A joule is equal to a kilogram times meter squared per second squared. But we aren't always going to use the joule because it's not the most convenient all the time. So we'll often actually use this other unit, the liter atmosphere. And this is not some special thing. It's literally just liters times atmosphere, so volume times pressure. And it turns out if you take volume times pressure, you can actually get back to these base units for the joule. And so a liter atmosphere, though, is equal to 101.32 joules. We're going to use this a lot in chemistry, and you'll see why as we get into actually using energy in a minute. And then the last unit is what's called the calorie. So you've seen a calorie before in your life, I'm guessing, if you've ever looked at a food label. 1 calorie is equal to 4.184 joules. And 1 calorie is specifically defined as the energy needed to raise the temperature of 1 gram of water by 1 degrees Celsius. Now, an important note about the calorie that's kind of weird is so they or so the lowercase calorie is equal to 4.184 joules. But a food calorie is actually an uppercase C calorie, and that's equal to 1,000 lowercase c calories. It's a really good system. So in some places they use the kilocalorie, which is the lowercase calorie with the K in front of it, and that's equal to an uppercase calorie. But even that gets a little confusing. So if you read your food label and it says that one serving is 300 calories, what that means is 300 uppercase calories, which means 300,000 lowercase calories. All right, now in internal energy, often we're not just worried about a molecule, we're actually usually worried about a system, because as chemists, it's actually hard to investigate individual molecules, right? So we generally investigate the energy inside a sample, whatever sample sitting in our beaker or sitting in our container or whatever we're studying. So let's talk a little bit about systems. So we have our system, then we have everything around our system, which is our surroundings. If you take your system, you add your surroundings together, that gives you the universe. Now we are not part of the system, we are part of the surroundings. So the system is the part of the universe we're studying, and the surroundings is everything else. Now if a system is giving off heat, I can reach my hand down and I will feel that my hand is getting hotter. So I, as the surroundings, am getting hotter. What's happening to the system? Well, if the system is giving off heat, then the system must be getting colder. The reason I'm saying this here is to emphasize the point that whatever the surroundings are feeling, the system is actually feeling the exact opposite, right? So if the pressure in the surroundings is increasing, that's because pressure is coming out of the system. And if the system is decreasing in pressure, that must mean that the surroundings are pushing in on it. There's three types of systems we're going to be concerned about. There's the isolated system. An isolated system is like a soup inside a thermos. The thermos insulates it so heat can't escape, and there's a lid on it so that the matter of the soup can't escape either. So in a thermos, you have no energy transfer and no matter transfer at all. Now in real life, there's never a perfectly isolated system. So if I put hot soup in this thermos, unless left this thermos on my counter for a couple weeks, then the soup inside would obviously get to the same temperature as the surroundings. But we can often make isolated systems well enough that we can say they're approximately an isolated system. The next type of system is the closed system. So this would be like soup in a bowl with a lid on it. So with that lid, you're preventing any of the soup from evaporating. So no matter can escape, but the heat can escape pretty easily. So in a closed system, you have a set amount of matter, but your energy can go up or down. And then the last type of system is an open system. In an open system, this is like your bowl of soup with the lid off. You can add matter to it. You can add cheese to your soup. You can add some pepper. And some steam is going to be coming off the soup, at least if it's hot. And so matter is going to be in flux here. And heat can also move out of this system as it's equilibrating with its surroundings. Or you could even put ice in it to change the average temperature of it. Okay, so let's talk now about what I just talked about, adding ice and changing the energy. So the internal energy of a system can actually usually be pretty hard to determine. You'd have to understand all the bonds that are in this compound. So if you have a mixture like soup, yeah, that becomes really complicated because now we're talking about literally millions of different types of molecules, especially if you have any type of organic matter in there. If you have split pea soup, a pea has cells with tons and tons of different molecules in it. And any type of meat, same deal, tons and tons of different molecules in it. So it can be hard to determine the total internal energy. But what we're actually usually more concerned about is our change in energy, right? If I'm taking steam and boiling it to power a locomotive, I don't really care how much energy is in the steam. I care about how much energy I can get out of the steam. And so we're going to be worried about how much energy we're going to get, or how much energy change is going to be happening, because that change in energy is what we're going to be using to drive ourselves. So change in energy, right, is equal to our final energy minus our initial energy. I'm going to make a special point about energy here because it's important, but it's not directly obvious. Energy is what we call a state function. So our change in energy is only going to depend on our current and initial states, but not on how we change the energy, right? To give you an example of another state function, altitude is a state function, where my altitude here versus in Colorado is only going to depend on the altitude here versus the altitude in Colorado. It's not going to matter whether I drive from here to Colorado, or I walk, or I take an airplane, or I take a space shuttle. If I go from here to Colorado, my altitude's only going to depend on my starting and final altitude. So let's get a little more detailed into this state function thing for a minute, just so we can drive this point home. Let's say I'm in Denver and I want to go to Chicago. I can take a couple routes to get there. First, if I go from Denver and just take the I-80, I can get to Chicago in a fairly straightforward route, right? It's not a perfectly straight road, but it's close enough. I could also take a more meandering course if I want to see more sights. I could take the I-25 down to Albuquerque, see some turquoise stones and some cool art exhibits. Then I could take the I-40 over to Memphis and catch a country concert, some country music. Then I could take the I-55 up to Chicago, and once I'm in Chicago, can do something that is relatable to Chicago, which I don't know. Okay, but these two routes have certain things about them that are state functions and certain things that aren't state functions. So things that would be state functions are my change in altitude, right? My altitude in Chicago minus my altitude in Denver is not going to depend on which of these two routes I take. My total change in latitude and longitude are similarly only going to depend on where I start and where I finish, not on which route I take. Things that aren't going to be state functions in this case are things like the distance I travel, right? So if I take the I-80, that's about a 1,000-mile trip. If I take the 25 to Albuquerque through Memphis up to Chicago, that's about a 2,000-mile trip. So distance traveled is not a state function, but my change in altitude is. All right, so you're going to need to be able to identify what is a state function and what is not. Now let's get back to our internal energy here. So there's only actually two ways to change our internal energy, which is nice because it makes it a little easier on us, right? Those two ways are heat and work. So for whatever reason, heat is defined as Q. And I don't know where that letter came from, but it's what we use. And heat is the spontaneous flow of kinetic energy from a hotter thing to a colder thing. So heat always flows in one direction. So if I take a hot object and put it next to a cold object, the hot object is not going to get hotter and the cold object's not going to get colder, right? The hot object is going to get colder and the cold object is going to get warmer until they equilibrate. So why is that? Well, the hot object has a lot of kinetic energy, so its atoms or molecules are bouncing around with high energy, and the cold object has lower kinetic energy. So as the hot object's high kinetic energy things collide with the cold object's low kinetic energy things, they speed up the kinetic energy in the cold object. And so this energy is going to bounce back and forth between these two places until it reaches an equilibrium and everything has about the same average kinetic energy. Work, which we define as W, which is nice and convenient. Work is the exertion of a force through a distance. So if I have a block on the ground and I apply enough force to move it 3 feet, then my work would be the force I push against the block times my distance. So we often describe energy as our capacity to do work and or our capacity to transfer heat. Okay? Now let's talk about the signs of Q and W here for a second. I'll do this with a little diagram here where this teal ball or green ball is our system and this yellow area is our surroundings. So heat can flow into the system. If it does that, then the surroundings is giving up heat to give it to the system. So if our system is gaining heat, then our Q, our heat value, is going to be a positive number. It's going to be greater than 0. We call this type of process an endothermic process. So if your system is heating up, taking in heat, that's endothermic. But if your system is cooling off and giving up heat, sending heat out to our surroundings, then your heat is going to be negative. Your Q is going to be less than 0. We call this an exothermic process. So endothermic is heat going in, exothermic is heat coming out into our surroundings. So an exothermic, if I put my hand next to it, my hand will get hot. With endothermic, if I put my hand next to it, my hand will get cold. Now let's talk about work as well. So the signing for work is a little weird. We define work in a way, or it's sign in a way, so that if you do work on a system, so if you push a system, then the energy inside the system will increase, whereas the energy from the surroundings will decrease. So if I do work on a system, let's say I push a block, then the sign of work for my system is going to be positive. If the system does work, so let's say the system is a piston that expands to push something, then the system is exerting some of its energy to push that. And so we'll say that the work is negative there. So if we have negative work by the system, the total energy of our system will be decreasing. Okay. Now, endothermic and exothermic are only referring to heat, not to total energy or to work, just to drive that point home. So let's go ahead and practice this idea and see how you're doing it. Tell me which of the following processes is exothermic? Chicken defrosting in the microwave, bread baking in the oven, a lake freezing over, soup warming to a boil on the stove, or sweat evaporating from your forehead. Go ahead and pause the video now and try and figure that out. All right, well, we know that heat always flows from a hotter to a colder object. So when you're trying to solve a problem like this, you want to figure out which is hotter, the system or the surroundings. What is your source of heat? Is your source of heat the system, or is your source of heat the surroundings? And that'll help you figure out what direction the heat is flowing. So if we look at chicken defrosting in the microwave, the chicken is cold and we're heating it up, right? We're putting energy into it using microwave radiation. That radiation then is causing the chicken to absorb heat. This is an endothermic process because the system is increasing in heat. The same is true if you're baking bread, right? You mix your ingredients and then you put it in the oven. The oven imparts heat into your bread. So your bread is taking in heat during this process. So this is also endothermic. And soup boiling on the stove is another very similar process where the stove is pushing heat into your soup and giving it energy so that it can boil. All right, so soup boiling is also an endothermic process. This last one, E, sweat evaporating from your forehead, this one is a little tricky. And it actually is very related to the boiling on the stove. So if you have sweat on your forehead, what is your system? Well, your system is not your forehead. Your system is the sweat. But we're going to figure this out by asking what happens to the system. So if I have sweat on my forehead and a breeze blows by, that sweat is going to evaporate and I'm going to feel colder, right? That's the whole purpose of sweat. It's designed by God to cool our bodies when we get hot. So as that air blows past you, the skin on your forehead gets colder. If your skin is losing heat, what does that mean for the water, the sweat? Well, that must mean the sweat is gaining the heat. So your sweat is gaining that heat, and that heat is actually allowing it to transition into the gas phase. So sweat evaporating is endothermic as well. The process here that's exothermic is actually a lake freezing over. Now this is a little weird, but if we think about it, what's happening to the water in the lake as it's freezing? The water is losing its heat, often to cold air around it, right? You have cold air above this water. The air is going to be absorbing the heat from that water. And so the heat in the water is going to be decreasing. It's going to be giving it off to the surroundings, so it's going to be exothermic. All right, so we've talked about at least two phase transitions here. So the soup boiling is another one that we kind of glossed over, but with the sweat and the lake freezing. So let's get into our phase transitions. So anytime you're going from a more ordered state to a less ordered state, so if you're going from a solid where everything's held in place and it's all very structural, to a liquid where now things are moving about, or even to a gas where things are just randomly chaotically bouncing around. So anytime you go to a more chaotic system, that is going to be an endothermic process. So you'll notice that these blue arrows, or they look green to me, but these blue arrows are all going to be endothermic processes. So what's actually going on there? Why do you have to put energy in to get more chaotic? Well, at low temperatures, you've got all these intermolecular forces, right, that are holding your molecules together. Those forces are strong. And so your system has to absorb energy to overcome those interactions so you can get into a more chaotic system. So part of the energy here is actually not going into increase our kinetic energy at all, but actually just to overcome our intermolecular forces. We'll talk more about this in the next lecture. But then if we're going from a more chaotic system to a less chaotic system, this is going to be an exothermic process, right? As a liquid freezes into a solid, the liquid is giving off heat, and therefore this is an exothermic process where it's becoming a more ordered system. So in that case, we have energy to overcome those interactions, but that energy is sapped away by our surroundings, and our molecules get locked in place as a result of this exothermic giving up of energy. All right, now let's talk about work. So that's what we've talked a bit about heat. Let's talk about work now. So we said this is force times distance. For a gas, we actually are going to use pressure for our force and our change in volume for our distance. Now you might look at pressure and change in volume and say, that's not exactly force and distance. And you're right. But it turns out if you multiply pressure times volume, or pressure times our change in volume in this case, it's actually going to give you the same units as if you take force times distance. So in chemistry, the work we're most interested in is generally work done by gases, right? So in your combustion engine, what you're doing is creating a gas, a really hot gas that pushes the piston in your car. And so most of our work that's done is in the form of gases. And this is the type of work we call PV work because we're taking pressure times volume. Now, like I said, the way we define the sign for work is a little weird, but the way we actually define work itself is almost even weirder. So if a system is doing work, we're going to define the work the system is doing as the negative of the external pressure times our change in volume. So this external pressure, so let's say we have a balloon expanding, then the balloon is going from a small volume to a bigger volume. So as it's expanding, it has to push on the surrounding atmosphere. So that surrounding atmosphere is resisting us, right? It's applying some pressure. And so the way we find our work is by taking our change in volume times our external pressure. That'll tell us how much work we're doing and how much energy we're losing as a function of that work, right? And of course, remember that delta V is our V final minus V initial. Anytime we have a delta, it's just final minus initial. So the way this is defined, if our delta V is negative, that means that we've gone from a larger volume to a smaller volume, right? That means that the surroundings are doing work on us. The surroundings are compressing our system. So in that case, the surroundings are imparting some of its energy into our system. So we get a positive work, which increases the energy of our system. If delta V is positive, that means we're going from a smaller balloon to a larger balloon, or from a compact piston to an extended piston that's pushing something, then our system is doing work and it's giving up energy, so it will have negative work. Okay? Let's give you a practice here. Let's have you calculate the work associated with the expansion of a gas in a cylinder from 50 liters to 75 liters against a constant external pressure of 10 atmospheres. All right, so for this part, remember that our work is equal to our negative P external delta V. Go ahead and pause the video real fast and try and figure this one out. All right, for this problem, we're really just plugging numbers into an equation, right? Our external pressure is 10 atmospheres, as listed in the question, and our delta V is just 75 liters minus 50 liters. So if we plug all that in, then we should get negative 10 atmospheres times 25 liters, so we should get negative 250 liter atmospheres. So now, if we define our work this way, it becomes really obvious why we like liter atmospheres as a unit of work. Or unit of energy instead of the joule, right? Because we were already in liters and atmospheres. Now, why do we care so much about PV work? Well, like I said before, it's because we use it for everything. All right, so we've got delta E equals Q plus W, right? And we've just said that W is generally equal to negative P delta V, at least in chemistry, that's the way we care about it. And so our delta E is going to be equal to Q minus P delta V. Well, let's practice with this equation here. Let's say that we have a balloon left in the sun on a hot day at the beach, and it's expanding because it's gaining heat, right? If the balloon expanded from 1 liter to 1.1 liter after absorbing 20 joules of energy from the sun, what are Q, W, and delta E for the air inside the balloon? And I'll give you a conversion here. The 1 liter atmosphere is equal to 101.32 joules. Well, let's start with our heat. Well, our heat is just 20 joules here. That's the amount of energy we absorbed from the sun. Notice that it's plus 20 joules. That means we absorbed the energy instead of giving off the energy. Now, what is our work? Well, our work is equal to negative P delta V, where P is our external pressure. We're at the beach, so our external pressure is 1 atmosphere. And then our delta V, we're going from 1 liter to 1.1 liter. So that would be 1.1 liter minus 1 liter, or 0.1 liters, times negative 1 atmospheres. So our work is going to be negative 0.10 liter atmospheres. Now for delta E, right, we're going to have to combine our Q and our P delta V. And so to do that, they need to be in the same units. Right now, Q is in joules, and work is in liter atmospheres. Now we could convert from liter atmospheres to joules or from joules to liter atmospheres. Either one is fine. In this case, I'm going to go from liter atmospheres to joules, so I'll just take that negative 0.1 liter atmospheres times by 101.32 joules per liter atmosphere, and that'll get me that about negative 10 joules of work being done. So now I can take my Q and add it to W. That'll get me my delta E. So I got 20 joules minus 10 joules. And so I have a total change in energy of my balloon of 10 joules. So I absorbed 20 joules of energy. I got rid of some of that by doing work on my system. All right, the last thing we're going to talk about in this lecture is something called enthalpy. Now, enthalpy is a weird thing because it's not a real thing. It's a value we came up with that's useful in a lot of other equations. Okay, so our enthalpy, H, is just equal to our energy plus our pressure times volume. And we can't usually measure our H, our enthalpy, very directly, just like we can't usually measure our energy, our total internal energy, very directly. So we usually only care about our delta H, and our delta H is equal to our delta E plus delta PV, right? So our change in enthalpy just depends on how much the energy and pressure and volume change. Now we've already said that energy is equal to heat and work, and we already said that work is equal to negative P delta V. And so when we're dealing with a constant pressure, and this only works when we have a constant pressure, These two terms cancel out, and our delta H is just going to be equal to our heat. And we're going to get to use this delta H in terms of heat a lot in later lectures. So at constant pressure, our delta H is just equal to heat. If we have a delta H greater than 0, that's going to be an endothermic process. Delta H of less than 0, it's going to be exothermic, right? And our subscripts for delta H are going to be useful in determining which process we're talking about. Now, the reason we like delta H's, or at least one of the big places we like them, is in phase transitions. So it turns out in these phase transitions, like we've already talked about, we have some delta H associated with this phase transition, or some heat associated with this. And so the heat, for example, for going from liquid water to water vapor is plus 40.67 kilojoules per mole. So we call this value, this heat of transition, our delta H of vaporization. And then if we're going the other way, if we're going from water vapor to liquid vapor, this would be our delta H of condensation. And that's actually going to be equal but opposite to the value of our delta H of vaporization. So we're working on the same process, just going in opposite directions. And so we're just flipping the sign there. But we'll get more into our enthalpy of phase transitions in our next lecture. All right, if you have any questions about any of that, feel free to reach out and let me know.